So in this video, we're going to be looking at how we can turn carboxylic acids into acyl halides, specifically acyl chlorides or acyl bromides. Here you can see that if we use SOCl2 or any other alternative delivery or chlorinating agent, I should say, that's what these are called, chlorinating agents, we're going to get an acyl chloride. However, if we use phosphorus tribromide, that's a bromine delivering agent, and we're going to see that we get a acyl bromide. Okay, quite simple. Let's get into the mechanisms of each respectively. We'll start with the acyl chloride formation from SOCl2. We won't look at the other phosphorus containing chlorine delivering agents just for simplicity here. And you'll probably only be tested on this one. Okay, so it starts with our SOCl2, which looks like this. And what's going to happen first is that OH group is going to initiate an attack by kicking up electrons to the carbonyl, which is going to allow for that carbonyl to attack, right? We're pushing the electrons forth onto the oxygen, so it's like, oh crap, gotta grab something. Most times it won't do that, but for dramatic effect, we're gonna say it's getting pushed electron density onto it, and it's just gonna grab the SOCl2. So that's exactly what happens. So we have a very unhappy OH with the double bond. And as we attack the sulfur, we don't want sulfur to get a negative charge. That's not good. So oxygen on the double bonded oxygen is going to take on that negative charge. And yeah, pretty simple. Oxygen, well, the molecule will always strive to go towards less electrical charge. So what happens here is this oxygen's going to curl in its electrons to make a carbonyl and kick out a chlorine. And now I'll bring it down here. So now we have this leaving group here, which is kind of good, but we can't have it leave quite yet. That chlorine that was just around proximity effect, it's going to attack our carbonyl unhappy hydroxide and leave us with an OH. So we're going to have OH, chlorine, and that decently good potential leaving group. So what happens next is these carbonyl electrons fold in, kick out, okay, and now we get the unhappy carbonyl once more, okay? Okay, so now our unhappy hydroxyl group, well, this has a negative charge on it. It doesn't want to give that negative charge to sulfur, so it's just going to pick up a hydrogen. They kind of work together, these oxygens, and they make our final acyl chloride. Okay, so that's the mechanism for that. We go through this whole process to get this, and now let's look at our PBr3 mechanism. So PBr3 looks like this. Okie dokie, same kind of spiel. We're gonna do that whole kicking up of electrons. It doesn't really happen this way. There's probably a step in between, but it's more dramatic this way, and therefore it's better. We attack the phosphorus and immediately kick off a bromine. Okay, so we get minus bromine. Okay, so we have a happy bromine. We have a happy group up here, but an unhappy group here. So bromine that just left is going to come back by the proximity effect, attack the carbonyl, and make a hydroxyl group. So we get this here. okay? And, oh my goodness, I almost got cut off there. That would have sucked. Okay, so our next step here, and I'll go on this side so you can see. Our next step is that carbonyl. It's like, I was unhappy. I'm a depressed fellow. I'm gonna keep doing it. It won't kick out the bromine. It will just be by chance that it will kick out this one instead. If you do happen to kick out the bromine, you're back to here. So it's just an equilibrium kind of thing. But we're saying that the product here is going to kick off this group instead. Okay, so it does that, and we're going to get a very similar intermediate, almost the exact same, just with bromine in it. And our, again, with those, no, what am I doing? Almost added too many bromines. With those groups below the oxygen, the nitrogen, the fluorine, all that, those elements they can't really support a negative charge in this manner, okay? When it's oxygen, phosphorus, that orbital overlap is garbage, okay? So it's not gonna fold in and have phosphorus have the negative charge if the more electronegative oxygen can just hold on to it. And it's still a reactive molecule, don't get me wrong. A negative charge is a negative charge, and that's bad. So what happens is, okay, oxygen is going to keep that really high negative electron character. It's going to pick up the hydrogen and lead to just a carbonyl. So could I put the cap on these damn markers? Okay, so we deprotonate our carbonyl, leading us to our acyl bromide. That is the mechanism for that. Let's just summarize. They're kind of similar. We first need to form what I call unhappy hydroxide, where we have a double bonded, or I should say a protonated carbonyl would be the correct term, right? It's a carbonyl, but it has a hydrogen on it. It's going to use that pushing of electron density onto the carbonyl to kick off a chlorine on the group, or a bromine here. And what that will do is allow a free nucleophilic bromine or chlorine, respectively, to attack that unhappy protonated carbonyl, which then down term leads to a leaving group. So in this case, SO2Cl, or what's this one? PBr2O, or OPBr2, I should say. And then we have our unhappy protonated carbonyl once again. So our leaving group comes back with a negative charge that can't be well stabilized by any other means other than that oxygen to pick up a hydrogen, and that's exactly what happens for both, and we get our acyl bromide and acyl chloride respectively. Hope you guys enjoyed and found this helpful. If you did, please like, subscribe, or comment if you have any questions. I'd love to answer them. Have a wonderful day.